formal proof revolution. Over the past decade, AI and interactive theorem proving have made huge progress. Recently, this progress has been getting a lot of media coverage. For example, the idea of using large language models and chatbots as sort of mathematicians' co-pilot or co-assistant is now a real possibility. Here, for example, it's been reported by the Scientific American. Terence Tao recently gave a very interesting talk at Oxford University about the potential of AI in science and mathematics. Moreover, there has been a particular focus on solving mathematical Olympiad problems with AI. And currently in mainly Silicon Valley, there's a competition between different companies to be the first to train an AI model to achieve a gold medal in IMO. I think, so for example, Google DeepMind is heavily involved in this and a few other startups as well. Right. Of course, interactive theorem provers have been an important part of this. The reason is interactive theorem provers on top of so they complement AI systems by verifying and checking the correctness of statements. So one of the common problems with AI systems and LLMs essentially is the problem of hallucinations. So essentially, they give you a piece of, they give you a solution which looks like something, something correct, but in fact, it's not correct once you start inspecting the details of that. And so this is a common problem with all of the large language models. And interactive theorem provers or proof assistants complement or try to solve this problem by instead of asking for natural language output, you are going to ask for formal output. So this is like a formal code mathematics that can be checked by one of these theorem provers. Broadly speaking, I want to subdivide interaction of AI in mathematics into like 3 categories. So the first would be machine learning for mathematical discovery. This is where we use machine learning to discover new mathematics. So we can form new conjectures. We can come up with counterexamples, for example. This has already been useful in graph theory, combinatorics, and knot theory. In the second, so this is where we formulate conjectures or discover counterexamples. The second category is where AI and mathematics interact is the mathematical foundation of AI itself. So this is where we want to basically understand the AI black box, or so you might have heard of terms like explainability of AI or interpretability. So here we try to classify AI architectures using mathematical models. It can be topological models, and recently category theory has been very useful in sort of like understanding AI architectures altogether. And the third place where AI and mathematics interact is, broadly speaking, this formal verification of mathematics or interactive theorem provers. So here where we want to digitize mathematics, but we also want to formally verify our digitization. So there has been many theorem provers that have been there for the last 50 years, more or less. And now there has been a resurgence of interest in these theorem provers coupled with advances in AI. So for example, AI can add auto-formalization where you take a piece of like natural language mathematics, like let's say you train your large language models on all of archive or math overflow or any database of large database of mathematics, and which are usually in natural model, mostly in English. And then you can also auto-formalize these things so that natural language input becomes a formal output written in one of these formal languages like Lean or Calc. And And then so at least you can write the statements of the theorems that you care about in that regard. And then the next step would be formalizing the proofs as well. Another really powerful aspect of AI in theorem provers is what we call copilot or auto-completion. So a user is interacting with inside Lean, trying to formalize some piece of code or trying to formalize their theorem. And in the middle of the theorem, you can use one of these copilots like Microsoft GitHub Copilot or many others that have since come out to sort of like get suggestions from AI or autocomplete your proof. And of course, we also have set solvers and SMT solvers for fully automatic proof finding. So it is the last category. So the third category that I'm going to focus on this during this talk. So let's have maybe a working definition of like a very basic definition of interactive theorem prover for people who are not familiar with these tools. So an interactive theorem prover, or for short ITP, is a computer software that can reason with mathematical definitions. So this means it can also reason with mathematical theorems and proofs, and these are usually provided by a user. And so the user writes definitions, theorems, and proofs in a language that the system can understand. And then the system in turn checks the correctness of those statements and proofs. So interactive theorem provers have been around since at least 1968. The first one is Automath, invented by De Bruijn. And then Mizar, which is based on set theory. And maybe the most recent one and the most popular one is Lean 4, which is based on dependent type theory. And I'm going to talk about this during the talk. So over half a century, so there has been a half a century of design and improvements that has gone to development of ITPs, and lots of ideas from like foundation of mathematics and type theory has come into this design process. So here's a sort of like a schematic picture of like what an ITP consists of, or in this case, Lean. So it is, it has a bunch of components. It has parser, it has an elaborator, kernel, and compiler. So essentially, kernel is maybe the most important part, which is it's the part that validates every inference step that you make in your proofs, and make sure that the proofs are correct. So it checks every inference step, and then therefore, once then it gives the guarantee of correctness for the whole proof. However, the kernel is usually kept to very small system of rules of reasoning. So usually it's like the order of like 300 to 400 lines of code, so which is not much. And this is extremely small. The reason that it's very small is because we want to, we want to be efficient essentially. So we want the systems to be fast in reasoning. So it's almost impossible to express any kind of like mathematics into the kernel itself. That's why we need the other parts, which is like elaborators and parsers, so that the high level kind of mathematics that you write, like let's say you're working with manifolds or geometry or whatever, at the end you want all of these things to be compiled down to the kernel so that the kernel can check that. So parser and elaborator help you with that. So this is like sort of like system point of view of Lean. But of course, Lean as an ecosystem itself offers more features. So there is Mathlib, which is the sort of like unified central library of formalized mathematics in Lean. So it spans many fields of mathematics. It's currently approaching 1.8 million lines of code and 800,000 theorems, covering many fields of mathematics. And then we have Lake, which is the package manager for Lean. So so we can always remain for taking care of like compatibility of different versions of Lean and so on and so forth. Reservoir essentially extracts training data from Mathlib for purpose of large language models trainings. And then we have a very active community for people who start with Lean, who are new beginners, and people who are more advanced and have been in this field of formalization for a long time, and who are leading projects, and we try to also help beginners. So if by the end of the talk you get interested in Lean, then I encourage you to join this Zulip community. And so here's maybe a cartoon picture of like how Lean looks like. So like every node, essentially, it's so representing a file in this Mathlib library. So for example, some of these things are annotated, like, I don't know, group theory subgroup.basic. So that's a file in Mathlib, right? And we have many thousands of such files. And of course, there's interdependency between these files because, you define a concept in terms of other concepts. And so this graph is auto-generated. So we have tools to auto-generate dependencies. And also, if we want to zoom in, we can do that. Right. Now, so if you get interested, here are some resources for learning Lean. So if you really want to dive into Lean very fast and right away, the first two resources are maybe the most appropriate. So natural number game, which is like you play a game which is completely web-based. So you don't need to install anything. You can just right away go to to that URL that I put there on the slide, and just play. So it's a game that you learn how to prove things about natural numbers, or how to define like operations on natural numbers using Lean. And then we have also a game on linear algebra. So it's a little bit more advanced than the natural number game, but then maybe it's more interesting. You prove more interesting theorems. And if you go to that website, you will see also other games like in logic and set theory and other parts of mathematics as well. In terms of textbooks, we have now 3 textbooks which have become sort of canonical. So there's a Mathematics in Lean textbook. We have Theorem Proving in Lean, which is more, learning the fundamentals of Lean and the logic behind it. And also the Mechanics of Proof, which is, a more sort of like easier like approach. It's more for like undergraduate teaching compared to Theorem Proving in Lean. So in terms of like how does Lean like help you in doing research, or what are the features that is relevant for research mathematics is so first of all, like once the definitions and proof are machine checked instantly for you, then you really, I mean, once you prove these things, if somebody else wants to use your work, they don't need to trust you, right? So the machine does that part, and therefore we remove a barrier for large scale collaboration. So suppose you work on a project and somebody else that you don't know from somewhere else in the world has proved something, right? You really don't need to know like the level of mathematical maturity they have, or whether like you don't need to check their proofs step by step. So you can just take that as a machine code and just build on top of that. So it does remove the trust barrier. And besides the certificate of correctness, it also offers like many more like helpful features, such as like now we have a unified central library, right? So so like if you want to define a concept, like there are not there's just one standard version of a definition for that concept. So that helps us to find more easily where things are. Then you have syntax and semantic search in Mathlib. So these are the semantic search is powered by AI. So let's say that you want to know, like, you have a theorem in mind, like roughly what it should say, and you don't know where in this gigantic library that is located. So you can just go to this. So we have some tools to search for theorems by natural language prompts, essentially. Also, like Mathlib offers you a sort of dynamic selection of level of details. So if you understand something, then you can use something, right? You can use the formal counterpart of what you want to use. But if you don't completely understand all the parts, you can always click through different definitions, and these are like digital artifacts. So you can get to the bottom of definition until like the very foundational level where like sets and numbers are defined and things like that. Moreover, the documentation and dependency graphs and blueprints, all of these things are very much auto-generated from the code itself. And this is benefit of digitization. You can also write custom notations, custom tactics, proof automations, using the metaprogramming in Lean. So this is where like we take proofs as like objects themselves. So you formalize something, right? So therefore it becomes like in Lean language. But then you can take that proof itself as a mathematical object or as meta-mathematical object, let's say, and then manipulate that one as well. And this is what we call usually metaprogramming. So this metaprogramming also gives you the ability to write domain-specific languages. So you can embed, for example, let's say you write a domain-specific language for Euclidean geometry, right? So you don't want to interact with all the foundation of Mathlib, but you just care about like, let's say Euclidean geometry. Then you can write a type system for Euclidean geometry and embed that type system inside Lean. Then you will write a compiler that will take Euclidean geometry type theory to the type theory of Lean. And therefore, the user doesn't need to really interact with all of Mathlib as such. And then moreover, as I mentioned before, we have this AI-powered completion, suggestions, and auto-formalization. Okay, so that was like a prelude to the talk. And now I want to give you a sense of what I'm going to talk about for the rest of the talk. First, I'm going to do a short demo to just give you a sense of how Lean looks like and the underlying language. And this part is I want it to be very interactive. So if you have any question during that part, please ask, interrupt me anytime. Then I want to show you how formalization in Lean looks like and some examples of large-scale collaborative projects that have happened in the past years. And finally, I want to get to this project that I'm leading about doing synthetic homotopy type theory in Lean. So I would like to start first with the language of Lean, and yes, please interrupt me anytime that you want to, zoom into something more. Okay, so I'm going to now switch to my Visual Studio Code. If my computer works properly, let's see. Right. Okay, so here we are going to look like basically how Lean looks like and how we can use it. So as I mentioned before, Lean is based on dependent type theory. So I'm going to spend a little bit of time to spell out what dependent type theory is for people who might not be familiar with this. So dependent type theory is an alternative foundation for mathematics. So you might have worked with, so as mathematicians, we usually learn set theory quickly in our undergraduate education. But maybe type theory is not something that, maybe if logicians among you might have heard you, but like most mathematicians are really not exposed to type theory. But actually, in my opinion, like dependent type theory is a more natural foundation to do mathematics in than set theory. And we can discuss it later, but so I'm going to tell you how that is, how dependent type theory is naturally a foundation for Lean and how we can use it. So this means that in Lean, everything is an expression or term, and every term has a unique type. And moreover, in dependent type theory, we have terms, types, formulas, and proofs. And all of these things happen in the same language. And moreover, there is a correspondence, so-called Curry-Howard correspondence, which basically says you can always, in this setup, interpret propositions as types and proofs as terms. So really, what we have is really types and terms, and we get propositions and proofs sort of as free. So here's like maybe the first how we define constants in Lean, right? So here I'm defining an expression M, and I'm saying that this M should have type of natural numbers. And then I define M to be the constant 1, right? So, so this is how you write in Lean. And on the right-hand side, you have sort of like so-called Lean info view. That is where like the interaction with the proof assistant actually happens. So right now, when I wrote this line, Lean says the result is, of type natural numbers. So I just defined an object which has type natural numbers, right? And similarly, you can do it for, you can define an integer and you can define a Boolean, so on and so forth. And then we can always check the type of an expression, right? So for example, once I define M, I can check and find the type of M. So the info view tells me that, in fact, M is a natural number, and N is an integer in this case. So then the question is, so what about N itself? Because, so we said like everything is an expression. So, and, natural number itself is an expression, so it must have a type. And indeed, Lean tells us that natural number itself is a type. So the type of N is type. So basically, this type is type of all sort of like small types. And then we can continue this. So we can check, the type of type, and that itself is a type, but in a universe higher. So we have this universe hierarchy where we start with the type of propositions. So you can, for example, this expression 2 equals 2, it's a proposition. And in Lean, we understand that by saying 2 equals 2 has the type prop. And prop itself is a type. So this is, then the type of all types is, again, a type, but in one universe higher. So we get this universe hierarchy. And moreover, this universe hierarchy is parametric. So if I check type U so you can here declare universe variables, and then you can check type U, and Lean tells you that's an object or an expression in the type U plus 1. So that's like it's one universe higher. And you can actually work with these types without specifying universes, and this is where we use type star. So these universes are parametric in universe variables. So for example, we have type of lists. And so for any type alpha, the type of list of alpha, it's again a type, and actually is in type in the same universe U, right? But if you really want to restrict list, so to say like I just want to define list for types of level 0, then you can write a list.0. So that's going from type to type instead of so you just eliminated the universe variable. So what is a type? So I mean, I talked about this without even telling you what type is. Well, I mean, there is no definition of what type theory is, but we can we can describe what it should be, right? So so every type comes with 3 rules. It comes with introduction rule, elimination rule, and computation rule. So here's an example. So for any type alpha and beta, I can form a new type, which is the type of pairs of elements of alpha and beta. Sorry, this has to be alpha. And this one should be beta. So here I just declared 2 types as variables, alpha and beta. And I can check alpha times beta, and that's going to be a type. And the universe is maximum of universe of type of universe of alpha and universe of beta. And alpha times beta is just a short notation for product of alpha and beta. So this is how you form a type. And then here's the introduction rule. So if you got some term A of type alpha and B of type beta, then you can pair them up, and then you get a term of type alpha times beta. So that's how we introduce terms in the new type. And okay, so that's how we introduce, but how do we use them, right? So these are where elimination rules come in. So in this case, for product types, we have two elimination rules. The first projection, which tells you if you've got something in type alpha times beta, then you can project the first coordinate to alpha. And similarly, you have a second projection. And finally, we have the so-called computation rules. So computation rules tell you how the elimination and introduction interact. So for example, if I first introduce and then eliminate, I get the same thing back. So if I start, with A and B, and then I pair them up, right? And then I take the first projection, I get A back. And in fact, you can prove this in Lean. And this is maybe our first theorem so far that we have seen. It's a proof of equality of two terms. And you notice that I have written by here and REFL. So this by indicates that I'm going to start a proof environment. And REFL says it's a tactic essentially that says you can prove this by reflexivity. So what is reflexivity? Well, reflexivity says if two things are definitionally equal, I can prove that they are equal, right? So in this case, like the left-hand side is definitionally or judgmentally equal to the right-hand side. Similarly, you have a second beta rule for second projection. And then you can change the order, right? So you can first start with the term of type alpha times beta. Then you can eliminate the first or project the first coordinate. So that's elimination. Then you use the second elimination and then project out the second coordinate. And then you can pair them up, right? And the whole expression on the left-hand side is actually equal to what you started from, like P. And this is called eta rule of product types. So basically, this is true for all types in dependent type theory. So whenever you form a type, it comes with three rules of introduction, elimination, and computation. So I want to take a pause here and see if there are questions. Okay, if there are none, then I just continue. Moreover, of course, Lean supports propositional logic too. So here I declare some, propositions like PQR. So, and then you can have the usual, binary connectives and the negation and the constants true and false. And so this gives you, so it has the full intuitionistic logic. And in fact, it also supports law of excluded middle. So you get the whole propositional logic, first order propositional logic. And here's maybe how we actually prove things about logic, right? So the rules of deduction in Lean is just a variant of natural deduction a la Gensen. And we usually write proofs in Lean using tactics. So these are instructions that we give to Lean to construct a proof term for us. And usually a tactic block starts with this declaration by. So here, for example, there's a theorem, and this is the name of theorem. So it can be really anything. Can give it foo or whatever. In this case, I want to prove the conjunction is symmetric in its argument, or at least one direction of that. And here I'm saying, okay, if P and Q are propositions, then P and Q implies Q and P. Right? So let's think for a moment how we prove this in natural deduction. Well, we say, okay, so let's assume P and Q is true, right? So you do that by this tactic intro. So you say, let's say P and Q is true, and the witness for that is H, right? And now your goal is Q and P. Well, what you can do with H is you can break H into, you can get a proof of P and you can get a proof of Q, right? So that you do with this tactic R cases. So you break down H into H1 and H2. So you can think of this as a lean's brain, right? So the goal remains the same, but now your list of assumptions or hypotheses got changed. Before this line, you had only proof H, and after this line, so if you put your cursor at the end of the line, you've got H1 and H2. One proof of P and one proof of Q. Well, I mean, if we want to prove a conjunction, then, so this is where the introduction rule of conjunction comes in. And then you can say, well, I need to construct a proof of Q and a proof of P. So that's what the tactic constructor does for you, right? It says it subdivides your goal into two sub-goals. So now you've got the first sub-goal, which is intro.left. So from P and Q, you want to prove Q. And that you can do by, you can just copy H2, or you can just write, assumption. So the tactic assumption looks into the list of hypotheses and sees if any of them matches like the goal. And then you prove this, right? Or because you have two sub-goals here, so you can be more, efficient, I guess, and apply the same tactic to both of them, right? So you just write assumption, and therefore you don't need these two sub-goals. So that is a little bit shorter. Or if you want to really be short, then you can, at the same time that you introduce H a proof, you can break it up, right? So you can write maybe, I think it was it, if I remember correctly, R intro H1, H2. Maybe I need to give it a pattern. Well, then I don't need to do this, right? Okay. Great. So I wrote a tactic, I wrote a proof or constructed a term of this type, right? By using tactics. But what is the term that corresponds to this, sequences of tactics? So you can do that by using another tactic, which is show term. And show term essentially shows you the final term that this sequence of tactic blocks corresponds to, right? So I can now click here, and show term says the term that you get out of this proof is really this. So it's a function that takes a proof A. So this is like our H basically. Then it breaks A to H1 and H2. So it does case analysis and then swaps the order of H1 and H2 and gives it as a pair again. Okay, great. And of course, the same thing would work if you just, instead of theorem, you write a definition. And this definition is not and, but maybe pair sim or something. And this is what I meant by Curry-Howard correspondence, right? Oh, you can see that something is being suggested here. So this is because I have my Copilot on. So this is GitHub Copilot suggesting you this, so we can see if it's correct. Okay, so there is some small mistake here. So it uses cases, but this tactic doesn't exist. It's a bit of hallucination, but maybe if we change it to our cases, it does work. Well, in this case, what is the error? Well, it's not working for that. But maybe if we do something like exact, something like that, it works. So, and I don't need these elements as well. So as maybe a small example that Copilot actually is helpful, but not terribly helpful. So it does make a bunch of mistakes, and it's definitely not so efficient at all. So I'm going to turn it off for the rest of this talk and so disable completion for lane 4. Great. And so now that so here's your proposition, right? P, and here you have a type. I could have written also types so that to have maybe direct correspondence between them. So this is like proposition as type instance of proposition as type interpretation, where proposition becomes type and conjunction becomes product type. Right, and of course I could immediately write this as well as a function, right? Or ask show term to do that for me. So I can replace it by this function that takes P, breaks down P to P.1 and P.2 and then swaps them. Any questions? Great. And so we have this nice command explode that gives you a sort of like a natural deduction tree kind of proof out of this theorem that we proved. So you write just explode and seam, and then you get the whole, you know. Yep. Okay, so I'm going to skip this example. So far we have done propositional logic. We also talked about what the type system is, and so Lean supports simply typed lambda calculus. So you have functions like lambdas essentially. So here, for example, I'm defining a +1 function from natural numbers to natural numbers, right? So this is how you write function from that takes argument x and gives x +1, and of course this is going to be an expression which will have type net to net. So this is the type of functions from natural numbers to natural numbers. Then of course you can compose such function. So this is a function of two functions g and f composed, and moreover this is defined in terms of this definition function.comp, which is in Mathlib, I believe. You can use Lean as a sort of like programming language to write programs. So here we write the factorial function as a function from natural numbers to natural numbers. And so this function is defined recursively. So natural numbers have two constructors, 0 or successor. So on 0, we return 1, and on the successor of n, we return n +1 times factorial of n. And you can use Lean as a calculator to calculate what's factorial of 9. And moreover, you can sort of compose functions, right? So in this case, I'm taking list of numbers from 0 to 8, and then successively apply factorial to this list. So I should get a list of factorials, and that is factorial 0 to factorial 8, essentially. And then, okay, so you have a programming language, but you can also now reason about these programs, right? You can prove things about programs. So once you define your factorial function, you can prove that for every n, factorial of n +1 is at least 2 to the power of n. So I shared this file later, but for now I want to skip how this is done, except that so when you are here, maybe it's interesting to actually maybe before right here. So here, for example, at this stage of proof, our goal is this, right? N +1 times factorial of n +1 is at least 2 times 2 to the power of n, right? And in my hypothesis, I have an inductive hypothesis, which says the same thing basically, but for just n +1. This is because I use tactic induction here. So I've got like n and the inductive hypothesis essentially. Somehow I have to use this, right, to get to the goal. And maybe a strategy is that I can prove the left factor 2 is less than n +1 +1, and the right factor 2 to the power of n is less than factorial of n +1. So I need to use a fact from in the library Mathlib, right? That multiplication of natural numbers preserve inequalities, right? And okay, so if you have not really interacted with Mathlib and you don't know where these things are, because it's really a vast library, then you can use these semantic search tools that I was talking about. So in particular, there is this tool called #Moogle. So I literally wanted to find a theorem that at that stage of the proof proves this. So if I write #Moogle with the data string, then it finds some suggestions, right? So that means whatever is written here is what this expression proves. And then I have to inspect which of them actually matches closely to what I want. What I really wanted was this, right? Was the second one. So it's not that bad. It doesn't find it as the first option, but maybe if you tweak your prompt a little bit, then you even get the nat.mul le mul as the first option. By the way, reading of these names look a little bit like, maybe it's a bit puzzling, like why they are named like this. So it's how we read this, right? So from left to right. So we say if I have two natural numbers and n1 is less than or equal to n2, so that's the first LE. And so yeah, if I multiply them, so multiplication of less than or equal is less than their the first multiplication is less than or equal to the second multiplication. So we basically look at the goal, which is this one, and name our theorem based on what it says, which is basically multiplication is less than multiplication, less than or equal to multiplication. Another tool that we have here that is more syntactic, not semantic, is suppose you are here and you wanted to prove the same goal. And this is sufficiently simple that you might look for like automation tactics to search and find a theorem that proves this. So you can use this tactic apply question mark, which goes and finds a relevant lemma that can solve this, right? So if I write apply question mark, then it finds this, this lemma that we found it anyway. So I can just click on this. And now my goal became simpler, right? My goal becomes much simpler. And this I can prove by just a tactic called simp. Great. Right. So far we covered like the logic and the type theory, but I mentioned that Lean is based on dependent type theory. So I want to emphasize the dependent part. So in simple type theory, our functions go from one type to the other, right? Like from A to B. But in dependent type theory, this B itself can it's not a single type. So for example, you might have a type A and a type B that goes from A, so it's a dependent type, right? Depending on the input from A, it gives a new type. And then you can have a function like f that takes a value in A as input, and then returns the output in B of X. So the type of output is dependent on type of inputs. And if you do like things like for example in shift theory or when you work with vector fields, for example, you definitely are familiar with this kind of things that you want to compute the type of sections of a shift, for example. You definitely have these dependent functions there as well. So the same kind of like rules of simply type lambda calculus also holds for dependent functions, such as introduction and elimination rules. Right. And finally, to just wrap up the whole introduction to Lean language, in addition to universes, dependent function types, and inductive types, we also have 3 axioms. So one of them is called propositional extensionality. And what it says is that if 2 propositions are logically equivalent, meaning that A if and only if B, then you can prove A is equal to B as expressions, or as terms of type prop. So that means wherever you prove an if and only if statement, you can rewrite along that. So you can rewrite, substitute A for B or B for A. Out of propositional extensionality and quotient types, you can actually infer function extensionality, which says whenever you want to prove 2 functions f and g are equal, you can test them on all inputs, right? You can test the equality on all inputs. And then we have a classical axiom of choice, which makes Lean non-constructive. So this is the so-called global axiom of choice, which says if a type is non-empty, you can extract an element of that type. So arbitrarily, right, by choice. And of course, this also implies exist.choose, which says from a witness of existential witness, you can actually find an element. So this is Hilbert's epsilon, essentially. And then you can by Diaconescu, we have, and that's proved in Lean, that choice implies the law of excluded. So therefore, the whole logic is non-constructive. Right. And more relevant to this talk is that Lean supports something called UIP, or uniqueness of identity proofs. So this means if I have two terms A and B of some type alpha, and then I have two proofs that they are equal, then the two proofs P and Q, whatever they are, must be equal, right? And this is true by reflexivity, essentially because how equality is implemented in Lean. So this says any two terms of any type alpha are equal at most in one way. Right. And so this will become important for later during the talk. And finally, the last thing that I want to say about the language or fundamental of Lean is that we have something called structures. So let's say you want to define a notion of semigroup, right? So you can essentially structures are inductive types like natural numbers, but natural numbers has like two constructors, right? Like zero and successor. Whereas structures, usually in Lean, we define them as an inductive type with a single constructor. So so it's more like this paradigm, right? So here I'm defining the inductive type color prime, but using this make constructor. So the make constructor is a function that takes three colors, red, green, and blue, and gives three components and gives you a color essentially. And so here I artificially define my own notion of semigroup, which is consists of So think of this thing as sort of like a constructor of an inductive type. So you have a carrier, which is type, and the carrier actually has an operation on it. So it's a binary operation. So it takes two inputs and gives you an output. And furthermore, it's an associative operation. So these two parts are like, the kind of like data, and then the last part is an axiom, right? About that data. However, in Lean, so this is not typical of how we actually define structures in Lean, because this is not modular at all. So in Lean, for example, semigroup is defined in a different way. Maybe I can click and comment on this. So here we are in a file called Mathlib algebra group defs, right? So these are some algebraic definitions, basically. So we can see that semigroup is defined. So here, just think of class as a structure for now. So this is a structure that takes an input G, so that's just the base type or the carrier type. But then this structure extends another structure, right? So all this structure provides you is this axiom, really. It's the associativity. And the rest of it comes from what it extends. So if I click on mul itself gives you, the operation. So this is more typical of how we define things in Lean. This is a more modular way. We use type classes and we extend type classes. So for example, if I write a group here, then so print, in fact, prints all the fields of group, right? So you get like lots of things here. But you can already guess that from some of these fields that groups must be defined in terms of monoids, right? And maybe monoids are defined in terms of semigroups and so on and so forth. So that's how you construct a hierarchy of algebraic structures in Lean. Okay, so this was like a very short, brief intro to Lean, and I want to take a quick pause if there are questions about this. Great. If there are no questions, then I will continue with the slides. Right. So that means I have to change my sharing config as well. So for example, liquid tensor experiment is was an ambitious project that started as a challenge from Fields medalist Peter Schulze in 2020. So the challenge was to Lean community was, to formalize a very complicated part of the main theorem of liquid tensor experiment, which is a theorem by Schulze and Clausen about profinite sets and P-Banach spaces. So here you can see on the slides that the theorem liquid tensor experiment. So that's the last thing in the formalization. And of course, I omitted the proof here. So the statement, took 6 months for the Lean community to formalize the statement of the theorem, because once you want to write something, you have to define all the prerequisite concepts that it depends on. So that brought a lot of things to Mathlib as well. And after 2 years, the community, some of the names are listed here, and in general, I think it had more than 30 contributors. After 2 years, we had the whole proof and moreover, foundation of condensed mathematics in Mathlib. Second project is the Smale's sphere inversion theorem. So this shows you that you can actually do geometry based on this, based on dependent type theory of Lean. Right. This is how it's formalized. So theorem Smale says that there exists a function from real numbers. So the first argument real numbers is the space of parameters, but essentially it's saying like there is no homotopy from the two sphere to R3, which is that Kant MDiff is the way to say in Mathlib it's smoothly differentiable, which is smoothly differentiable, and it's at 0 is equal to identity function, at 1 is minus x, which means there is no, so this is the antipodes essentially. So there is no smooth differentiable antipodal function immersion from second sphere to R3. So this is the well-known sphere inversion theorem, and this was proved in Mathlib 2022. Then there is a more recent project started by Kevin Buzzard and 41 other contributors to this. It's the formalization of Fermat's last theorem by Wiles and Taylor. So this is ongoing, and I think it also, like, people can join this project. So it's an open project that anybody can join. Then we have the equational theories project by Terry Tao. So this is about, the goal is to describe sort of like implication graph relating like equational laws of some algebraic structure called magmas, right, in universal algebra. So it's sort of like, it's different than other project because there is no single theorem, right? There's no final single theorem that you are aiming for. It's more like crowdsourcing to prove a class of equations, right? So every equation is not too hard to prove, but you need like lots of contributors to do this. And of course, all of the graphs here are also auto-generated from Lean digital, from the digitized version, right, of the proofs. And we have Collison's theorem, which shows pointwise almost everywhere convergence of Fourier series of L-squared functions. So here, the graph that you see here is something called blueprint. So that is how we organize in Lean how, like if you do a sort of like larger scale collaboration, you want to delineate or point out which parts have already been proven, which statements have been formalized, or if some of the proofs are complete or not yet, so that people from all over the world can join your project, and sort of like you divide the labor this way. Some other projects, so we have independence of continuum hypothesis in Lean, capset problem, with vectors. We have finiteness of class group of global fields, model independent infinity categories, if you're interested in algebraic topology, and polynomial functors in Lean as well. And so this recent project that I also want to talk about, which is bringing synthetic homotopy theory into Lean. this is a very different project than before, and I want to take like 5 or 6 more minutes to talk about how it's different. So as maybe demonstrated by all these projects, Lean language is very flexible to do all sort of complicated mathematics, whether algebraic or geometric, right? However, for certain domains of mathematics, it might not be the easiest or the most efficient way to directly use Lean. So it might be better to if you work with like a certain domain of mathematics, let's say homotopy theory, to sort of embed a type theory that captures homotopy types, right, into Lean, and then work within that restricted language and write a compiler that compiles that restricted language to meta language, which is Lean. Because sometimes to restrict the language, actually, we can write more efficient proofs. And this is a field in mathematics that's been around for at least now 20 years, I would say, called homotopy type theory, which is basically using types to reason about homotopy theory. So first, I want to make a distinction between the synthetic and analytic mathematics. So in synthetic mathematics, such as like Euclidean geometry or Hilbert's formalization of Euclidean geometry, you have like some primitive notions like points, lines, planes, and things like that, right? But we never like define these primitive terms, right? We just like axiomatize them. So you can as well replace them with like chairs, tables, whatever, right? As long as the relation between them are satisfied. So this is a formalist approach to mathematics. And then in the analytic version, we actually work with specific models, right? So for example, you can pick the coordinate geometry. So therefore you fix coordinates, and then you try to reason with such coordinates. And then if you pick a different model, then it's not so clear that how proofs transfer to a different model. So you might start writing new proofs again. So the advantage of synthetic proofs is that make mathematical objects directly accessible, right? So you don't need to define points to work with points, as long as you know what axioms and relations it satisfies. So we directly work with objects instead of carving them out in models. We also don't get distracted or obstructed by particularities and specificities of models, right? So it might be something about coordinates that is not geometric, right? I mean, so you can use real numbers, or you can use hyperreals, or whatever you use to fix your coordinates, or you can use rationals. So right, and then usually like there are many models, and we don't have like a canonical model that we want to choose, or there is no categoricity. So then the question is like which one is better to choose. So doing synthetically, you don't have to face that question actually. And moreover, synthetic theorems and proofs are more conceptual and hold at high level of generalities. So there are many fields of mathematics where, in the last maybe 100 years has been a lot of attention to develop synthetic versions of those fields, such as synthetic topology and synthetic domain theory. Synthetic differential geometry, for example, is a famous case and has a rich history as well. And synthetic homotopy theory, which is like, instead of like working with specific models such as simplicial sets or Kant complexes or infinity groupoids, you actually you try to axiomatically say what homotopy theory is. So maybe quickly, for people, just reminding what a groupoid is. So a groupoid is a collection of objects and morphisms, right? Where you have identity morphism, you can compose morphisms, and then every morphism is invertible. Right. You can also phrase it saying a groupoid is a category in which every morphism is invertible. And then you can actually like define these things in Lean. So I'm going to skip this a little bit because for interest of time. But here essentially like this slide is how groupoids are defined in Lean. So it's using that hierarchy of structures, right? Starting from quiver, which defines the hom sets, between any two objects. And then the category structure, which gives you the identity morphism and composition operation. And then in groupoid, you add these axioms that, so first of all, a data that says adds inverse morphism to every morphism, and then two axioms that, inverses are left and right mutual left and right inverses. So in topology, we associate to every space the fundamental groupoid of that space, right? So the objects are points, the morphisms are homotopic classes of path in X, and the composition is induced by concatenation of path. So for example, this is how the fundamental groupoid in Lean is defined. So the first line, path homotopy quotient, essentially says like the morphism in this fundamental groupoid are path from X to Y, but quotiented out by the homotopy relation. So I don't want to go into detail of that definition, but just so that to say that we actually have these theorems in Lean, right? Like that the first fundamental groupoid of the first sphere, S1, is the groupoid of integers. So the groupoid of integers has, one object and z many or integer many loops, which are invertible loops essentially. And it's also proved in Lean that for n at least two, pi1 of Sn is trivial. So it's a trivial groupoid. So that means like that pi1 is not good enough to distinguish between homotopical data, right? Because it cannot distinguish between higher spheres. It just gives you the same trivial groupoid. So therefore, we need something better than fundamental groupoids. So we need fundamental infinity groupoids. So fundamental infinity groupoids, instead of just objects and morphisms, have higher data. So there are two morphisms which are like, homotopies between paths, and three morphisms are homotopies between homotopies, and so on. And then we define composition as, in a way, homotopy coherent concatenation of homotopies, because we have to define it at every level, and they have to be coherent. So you can imagine that how difficult this can be to formalize in Lean, right? So first of all, you have to imagine that you are trying to formalize these infinity groupoids, and then you have to formalize infinite amount of data, right? So what are the points, or what are the objects, morphisms, one morphism, so on and so forth. There's a way to do that, but even if you do this, the really hard part is to define this homotopy coherent composition operation for higher data. So homotopy type theory, it's again another foundation for mathematics. So this is also based on dependent type theory, but here we have a new principle of reasoning about identities. So it has a new identity type. So in homotopy type theory, which really started in 2013 during a special year at Institute of Advanced Studies. So and there's a textbook on this, which is on the slides. So in homotopy type theory, every type encodes the structure of the whole infinity group, right? So types encode spaces, and terms of the types encode point, and proofs of identities, like if I have two terms x and y, proof that P proves x equals y, that encodes the idea that there's a path in the space x from x to y. And then higher homotopies are also identities in identity types, right? Identities of identities. So this is the whole type system of homotopy type theory. It has some of the things we discussed in Lean, but crucially, in the low right corner, you have this complicated identity type. And this identity type is different than the equality type that we discussed in Lean. So crucially, in Lean, we had this uniqueness of identity of proofs, which said, if I want to prove two things are equal, then I can do that in maximum one way, right? Whereas in homotopy type theory, you actually have an infinite groupoid of ways that you can identify two objects. So the identity types in homotopy type theory are much richer. So the semantics of homotopy type theory has been worked. So there's been two decades of work on this. We have the first groupoid interpretation. So this is the one groupoid interpretation, but it's not complete because we needed to go to infinity groupoids. And then we had the full Voevodsky simplicial set model, which in fact gave the infinity groupoid semantics of these type rules that I just showed you. So in this project that we are doing, we are embedding this type theory into Lean. So that's the so-called, in the diagram is embedded type theory. Then we sort of like compile down this to an algebraic gadget called natural model of type theory, which I don't want to talk about in this talk. And this compiling down to natural models, then yet another time we are going to compile it down to actual classical models, like in groupoids or infinity groupoids or simplicial set models, right? So what is the advantage of this? Well, the advantage is in the embedded type theory, which is homotopy type theory, lots of proofs are much easier. So for example, we have a much shorter proof that pi1 of S1 is Z or pi4 of S3 is Z2, right? So it's just really a matter of few lines. Whereas like if you follow like classical proofs, like let's say from Hatcher's algebraic topology textbook, you have to develop theory of covering spaces and then use some prove something about certain universal coverings and so on and so forth to prove pi1 S1 is Z. So synthetic proofs are much shorter. Then what we want is to compile down the synthetic proofs in Lean to classical models that we know, right? Like to groupoid models and to simplicial models, and see that these synthetic proofs, in fact, sort of more or less agree with the classical proofs we know, or maybe they actually give new classical proofs, generate new classical proofs, right? So I'm more excited to do. So this is an ongoing project. I provided the links in the slides, few slides back. Yeah, we are looking for collaborators. So if you want to work on this, yeah, you're welcome to.